Swayam Prabha. Digital India. Educated India.
Welcome to another lecture of this course called Mathematics for Economics, Part 1. So, in the previous series of lectures, I think there were 3 lectures, we covered the basics of differentiation. So, we defined what is the derivative of a function and what is the Newton quotient. We had discussed a bit about the limits because the idea of limits is important to define differentiation and derivative. We also talked about rules of limits and rules of differentiation. So, what happens if you have the addition of 2 functions? If you take the derivative of that, then what do you get? Or if you have the difference of 2 functions and if you take the derivative of that, then what do you get? Product of 2 functions, and that we saw is called the product rule. We also talked about what is known as the quotient rule. If you have the quotient of 2 functions and you want to take the derivative, then what is the result? And finally, we looked at partial differentiation, because it may happen that a function has more than one variable as the independent variables, and if you want to find out how the function changes with respect to change in each of these variables, independent variables, then we get what is known as partial differentiation. So, those things have been covered. So, today we shall start with a related topic, and this related topic is called higher order differentiation and linear approximation. So, this is the first slide that we have. The derivative of a function is called the first derivative, or f dash of x, right. This is same as f dash of x is equal to ddx of f of x, and if you have y is equal to f of x, then you have ddx of f of x is equal to dy dx. So, this is called the first derivative, or f dash of x. This function f dash of x can be further differentiated to get the second or higher order derivatives. So, if you have f dash of x, then f dash of x itself is a function of x, right. F of x is a function of x itself, but if you take the derivative with respect to x, you get f dash of x. Now, f dash of x itself is a function of x. So, it can be differentiated further with respect to x, and if we do differentiation of f dash of x once, then we get the second derivative. So, second derivative is denoted by f double dash of x, right. So, you have 2 dashed here. So, we are calling it as the second derivative or double derivative of f x. There are other ways to denote the same thing. F double dash of x is d square f x dx square, or it is the same thing as y double dashed, and which is the same thing as d square y dx square, if we assume y is equal to f x. So, there are different ways to denote the same thing. Now, we take one example. Suppose this function is given fx is equal to 3x square minus 4x plus 6. So, this is equal to fx. We have to find the first and the second derivative of this function. So, fx is given 3x square minus 4x plus 6. So, we take the first derivative. We use the power rule, which is if we have x to the power n, and if we want to differentiate that with respect to x, then we get n multiplied by x to the power n minus 1. So, 3 multiplied by 2 multiplied by x, so that becomes 6x, and minus 4x. So, if you differentiate x with respect to x, you get 1. So, finally, you are getting 6x minus 4, because the derivative of 6, which is a constant, is 0. So, this is the first derivative, dfx dx is equal to 6x minus 4. Now, we want to find out what is the second derivative. So, for that we have to differentiate this once again with respect to x, and if we do that, we shall get d square fx dx square is equal to 6. The reason being that minus 4 will drop out because the derivative of a constant is 0, and if you want to differentiate x with respect to x, you get 1, and 6 is a constant. So, you have 6 multiplied by 1, therefore, you have only 6. If the second derivative is differentiated once more, then what happens? We get the third derivative, right. So, this way it goes on in an iterative manner. So, in the above example, if you have fx is equal to 3x square minus 4x plus 6, and from this we had obtained the second derivative to be 6. So, if I want to find the third derivative, I have to differentiate 6 with respect to x, and that is equal to 0, because the derivative of a constant is 0. So, the third derivative in this case is equal to 0. Now, this third derivative is also written as 3, instead of these 3 dashes, I just write 3 within brackets. So, f of superscript within brackets 3 x, or it could be written as d cube fx dx cube. So, this is the third derivative. And likewise, we can go on the order of the differentiation, and we get the fourth derivative, right, f superscript within brackets 4 and x, right, the fourth derivative, or d4 fx dx4, and this way it can go on, and we can write it for any arbitrary number n is any positive integer, and so it will be fn x or dn fx dxn. This is called the nth derivative of the function fx. This procedure of obtaining higher order derivatives can be performed for partial derivatives as well. So, this was a case where fx was a function of just one variable x, y is equal to fx. But if your function has more than one independent variable, then we know we can take the partial derivatives, and for partial derivatives also one can find out the higher order derivatives. So, let us take one example, a general case. Suppose y is equal to f of x1, x2, xn, right, is a function of n independent variable, and these variables are x1, x2, xn. Now, we know one can obtain n partial derivatives of first order from each of the n independent variables. So, this is written as del y del xi, where I can take any of these values. So, del y del x1 could be the partial derivative with respect to x1, then you have del y del x2, del y del x3, etc., etc., del y del x n. So, n partial derivatives could be obtained and all these derivatives are of the first order. The same thing is written as this, right, f dash I, and the independent variables are x1, x2 dot 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 xn, and the same thing can be written as del f del xi. So, n partial derivatives of the first order are possible. For each of the n first order partial derivatives, one can obtain n partial derivatives of the second order, right. So, this is how it is written. So, you are starting from this del f del xi, right. So, you have differentiated partially this function with respect to xi, and this thing del f del xi, it could be differentiated with respect to each of the independent variable, and let us assume that xj is that arbitrary independent variable. So, the expression that you are going to get is going to look like this: del xj of del f del xi, right. So, two partial derivatives have been taken, first with respect to xi and then with respect to xj. Mind you, I could be equal to j also, but it is not necessary that I is equal to j. I and j are any two arbitrary numbers less than or equal to n. So, this expression is written as also as y double dashed ij or f double dashed ijx, where if you notice this x that I have written here is boldface x, which basically denotes this vector. So, this vector. Okay. So, this is the second derivative. Now, how many second derivatives are possible from this function? In all, there will be n multiplied by n, that is n square second order partial derivative terms, right. And this is easy to see. From each of the n independent variables, you get one partial derivative of the first order, and from each of the first order partial derivatives, you can further differentiate partially with respect to n independent variables, and so from each of the n you get n more second order partial derivatives. So, in total n multiplied by n is equal to n square such second order partial derivative terms are obtainable. And this n square terms are arranged in an n by n matrix, and this matrix has a specific name. It is called the Hessian matrix, and this is how this Hessian matrix is written. You can see this matrix has n rows and n columns. So, each of these rows, suppose you take the first row, in the first row the first number in the subscript is 1, right. So, first the f function has been partially differentiated with respect to 1, and so you will get just one term. So, f of 1 x, right. Then this f of 1 x is differentiated partially second time with respect to each of these n variables. So, you are getting this whole range of numbers, n numbers, and this is performed for each of these variables, right, and you are going to get n rows, n columns. So, this is n by n matrix, and within the brackets these are the x's, right, and these x's are, as we have seen, these are vectors. So, this Hessian matrix is evaluated at this particular vector x, where x is equal to x1 x2 dot 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 xn. So, when we are dealing with a function with more than one variable and we are doing this this operation of partial derivatives, then we talk about second order partial derivatives, then this idea of a Hessian matrix becomes very important, because the second order partial derivatives are represented through this Hessian matrix. Now we talk about something else which is called the chain rule of derivatives. Suppose y is a function of the variable u. So, y is a function of u, right, but u itself is a function of x. Okay. So, y is called a composite function of x, because there are two functions involved here. One is the f function, which is a function of u, and the other function is the g function, which is a function of x. So, y therefore is called a composite function. It involves more than one functions of x. In this case, the change in x sets off a chain reaction first to u and via u to y. This is captured by the chain rule. So, this is easy to see. Suppose x is changing, then this is going to affect u, right, u is going to change, and therefore, if u is going to change, that will affect y. So, a kind of chain reaction is set off if x changes, and the effect of that chain reaction ultimately reaches y. So, this chain reaction is captured by this chain rule, which is written here: dy dx is equal to dy du multiplied by du dx. For the chain rule to hold, both y and u have to be differentiable functions. That is very obvious, because you have to be able to differentiate g with respect to x and f with respect to u. Only then you can talk about these terms on the right hand side of the chain rule. In words, what does it mean? It means that the rate of change of y with respect to x is the product of rate of change of y. This should be change. Rate of change of y with respect to u multiplied by rate of change of u with respect to x. That is what we have written, right. Rate of change of y with respect to x is equal to rate of change of y with respect to u multiplied by rate of change of u with respect to x. So, let us take one example to focus our ideas. So, suppose x is given as a function of small t, right. So, the specific form is this. It is a kind of complicated form: 10 multiplied by 1 plus root over t square plus 1 bracket close to the power 15. Okay. So, it is a function of t, but it is a little bit complicated function. So, we have to find out what is x prime t. So, the derivative of x with respect to t, that we have to find out, this dx dt. Now, we apply the chain rule, but before that let us define this function u. So, u is, suppose this expression inside the brackets, it is 1 plus root over t square plus 1. So, if I take u is equal to that term, then x t becomes 10 multiplied by u to the power 15 by the given function of x, and we apply the chain rule that x prime t, that is dx dt, is equal to dx du multiplied by du dt, right. So, what is dx du? Okay. So, that we can obtain from here. It will be 10 multiplied by 15 multiplied by u to the power 14. I am using the power rule, that if you take the derivative of x to the power n, you get n multiplied by x to the power n minus 1. And there is another term which is du dt. So, how the u changes with respect to change in time. So, here t can be assumed to be time. So, that is what we have written here. We have just substituted the value of u from here, right. U was assumed to be this. So, I am using that expression of u, which is 1 plus root over t square plus 1, that we have to differentiate with respect to t, and this is preceded by 10 multiplied by 15, which is 150 multiplied by u to the power 14. And now actually we have to use another function, right, another chain rule we will apply. To simplify this expression, we assume that v is equal to t square plus 1. So, within the root over we have now v, right, instead of t square plus 1, and we once again apply the chain rule, right. So, d dt of this thing will be d dv of this thing multiplied by dv dt, and d dt of this expression will be d dv of root over v, because 1 will cancel, 1 is a constant, multiplied by dv dt. And again I use the chain rule, which is you have v to the power half here, root over is nothing but half. So, half comes first and then v to the power minus half, half minus 1 is minus half, and which can be written as 1 divided by root over v multiplied by dv dt. Right. Now, we have to find out what is dv dt. dv dt is not known to us. So, from here I can find that here if I differentiate v with respect to t, again I use the power rule and I will get 2t, right, and I substitute that back in this expression and I get this x prime t is equal to, notice what I am doing here, 150 multiplied by half is 75, and then we have u to the power 14. So, I have just substituted back the expression for u here. So, u to the power 14 multiplied by 1 divided by root over v. So, this is root over v, okay, and multiplied by dv dt, which is 2t, right, and this can be written in this form, because 2 multiplied by 75 is 150, and I have taken t in front and the rest of the terms are same. So, you have this to be our answer. Okay. Now, here what we have done is actually we have extended the chain rule one step more. We have actually used this kind of formula, that dy dx is equal to dy du, du dv, dv dx, right. First we have used the u function, right, with a proper definition, and then we have used the v function here, right, with the proper definition, and there we got the expression for dx dt. Okay. Alternatively, the chain rule can be written as the following. Suppose y is a function of x and you have x is itself a variable, but it affects u, right. So, y as a function of x can be written as f of u of x, right, because u affects y, but x itself affects u. So, I write this as this, a function of a function, where y is a composite function with f as the exterior and u as the kernel. Kernel means something which is inside, and f is that function which is outside. So, you have basically two functions fused together. From this we write this, that y prime x naught is equal to f prime u of x naught multiplied by u prime x naught. So, you have basically two derivatives, right, like we have in the chain rule. First, f is differentiated with respect to u, but u is evaluated at x naught, and multiply that with the derivative of u with respect to x, where x is evaluated at x naught. Now we come to another kind of rule which is called implicit differentiation. So, we start with an example. Suppose this is given, x multiplied by root over y is equal to y 4. Here it is not explicitly mentioned y as a function of x. So, x and y are merged together, right. So, we have to find out what is y dashed, that is dy dx. So, what we do is that we take the derivative of both sides with respect to x and use the product rule and chain rule. So, if I take the derivative of both sides and I use the product rule first. So, the first function which is x, then multiplied by d dx of the second function which is root over y, plus the second function root over y multiplied by the derivative of the first function which is dx dx. And on the right hand side you have the constant, and if you take the derivative of the constant it becomes 0. And then what do? We basically now use the chain rule. So, there we have used the chain rule. First we differentiate root over y with respect to y and multiply that with dy dx, and the other terms are kept intact, right. Now, if I take the derivative of root y with respect to y, I get this expression, half of 1 divided by root y multiplied by dy dx, and the second term will just be root y because d dx of x is equal to 1. So, root over of y multiplied by 1 is root over y, and on the right hand side you have 0. And then I take dy dx to one side, which is what I need to find, which is y prime, and on the right hand side if I simplify this it will be just be minus of 2y divided by x. So, this is what I was supposed to find, y prime. So, this was the first derivative dy dx, but from this first derivative actually I can find the second derivative. But notice how we have proceeded so far. Although the function is not explicitly mentioned, y is not mentioned as equal to f of x. It is implicit, the y and x are merged together. So, implicitly y is a function of x, and we have just taken the derivative of both sides with respect to x and proceeded, and we have found the dy dx. Now, dy dx is this. So, I can from here find out the second derivative of y with respect to x by differentiating this expression minus of 2y divided by x with respect to x. And if I do that, I use the quotient rule now. So, minus of quotient, which is a ratio, on the denominator I have x square, right, the square of the denominator. On the numerator I have the denominator multiplied by the derivative of the numerator. So, 2y that I differentiate with respect to x, I get 2y dash minus the numerator multiplied by the derivative of the denominator, which will give me just 1. And what is y prime? So, y prime is substituted from here. So, I include that here, and if I simplify this a bit, I will get this expression 6y divided by x square. So, before we conclude this lecture, here are some examples from economics where I use implicit differentiation and also chain rule. So, here is the first example. So, you have c, which is a function of y. Remember how we named this function before. This is called a consumption function. So, this is in the context of macroeconomics. You have the total consumption of the economy, which is called the consumption function, and it is a function of the income of the economy. So, I have taken a very simple consumption function, linear, 100 plus 0.7 multiplied by y. And we know this identity that y is equal to c plus I. Y is output or income, which is equal to consumption plus investment. So, we have to answer 3 questions. First, find y as a function of I, find dy di, and find dy di for a general function c is equal to fy. Okay, let us go one by one. So, we substitute this particular function which is given to us, the consumption function, into this macroeconomic identity y is equal to c plus I. And if I do that, I get this y is equal to 100 plus 0.7 multiplied by y plus I, right. So, then I have to find out y as a function of I. So, what do? I take y to one side, therefore, I will get on the left hand side 1 minus 0.7 is 0.3, 0.3 y is equal to, on the right hand side you have 100 plus I. So, therefore, I take I divide both sides by 0.3 and I will get this particular expression for y. Y is equal to 1000 divided by 3 plus 100 divided by 3 multiplied by the investment I. Now, from the above, how do I find out the dy di? I can use this explicit function. This is not even an implicit function, this is an explicit function of y. And I differentiate this explicit function of y with respect to I will get 10 divided by 3. That is the answer. And the third part is, suppose the form of c is not given, c is just given to be a function of y, f of y, and I have to find out dy di. Now, how do I do that? I follow the same method as before. I substitute c is equal to fy in the macroeconomic identity. So, I will get this and I take the y terms to the left hand side and I get y minus f of y is equal to I. Now comes the role of the implicit differentiation. I differentiate both sides with respect to I, because I have to find out dy di. And if I do that, I get this term dy di minus ddi of f of y is equal to 1, because di di is equal to 1. And then I use the chain rule, right. Dy di minus of d dy of fy multiplied by dy di is equal to 1. So, I have broken this down into 2 parts. And then what is d dy of f of y? Let us suppose that is f dash of y multiplied by dy di is equal to 1. So, now I can take a dy di common and I get dy di multiplied by 1 minus f dash of y is equal to 1. And so, I divide both sides by 1 minus f dash of y and I get this expression dy di is equal to 1 divided by 1 minus f dash of y. Now, this is a very important expression in macroeconomics. This expression is often called the investment multiplier. So, what it tells us is the rate of change of income, which is the GDP of the country, if investment expenditure changes by 1 unit, right. So, it shows us the impact of investment on the national income. That is why it is called investment multiplier. And you can see it is a function of f dash of y, because f dash of y is coming in the denominator as a negative term. What is f dash of y? F dash of y is the rate of change of consumption with respect to income, and that we have seen is called the marginal propensity to consume, right, MPC. We have talked about this before in another context. So, MPC is something which appears in the investment multiplier, and you can verify that as MPC rises, then the value of the investment multiplier also rises. So, what it means intuitively is that if people spend a greater portion of their additional income in consumption, that basically increases the impact that investment increment might have on the national income. All right. And we have seen before that that this MPC should take a value less than 1, and you can now see why that is true. If MPC is equal to 1, then this term becomes undefined, it becomes 1 divided by 0. So, MPC to make this term meaningful should take a value less than 1. I now talk about another example where implicit differentiation and chain rule will be used. Suppose the demand and supply functions in the market are given by D. So, this is the demand function, quantity demanded is a function of price, and S, quantity supply is a function of price. Here A, B, alpha, beta, these are all positive constants. These are what we have talked about, is they are called parameters. But what is small t? Small t is appearing here in the demand function. It is not appearing in the supply function, mind you. Here T is the tax per unit of the good imposed on the consumers of the good. Okay. So, if you want to buy 1 unit of the good, then you have to pay this small t, and you are a buyer. So, you have to pay the money, not the seller. So, apparently the government is collecting this tax from the consumers by increasing the price, not price, the price is given, but the price that is paid by the consumer, that gets increased by this small t. Mind you, the money that the seller will get, it does not increase, it remains at P. So, the gap between P plus T and P goes to the government as tax. So, from the above we can talk about what is known as the market equilibrium condition, right, and this is just demand is equal to supply. A minus B of P plus T is equal to alpha plus beta multiplied by P. Now, we have to again answer 3 questions. Find dP dt from the above, that is how much the price change, how much does the price change with respect to T. So, that we have to find from the above equation, and secondly we have to solve P explicitly and find dP dt, and third, if capital T is the tax revenue, find its expression and find the T which maximizes the tax revenue. All right. Let us see how it goes. Now, this is the equilibrium condition, right, and differentiating both sides with respect to T. So, here we are using basically the implicit differentiation, and if I do that, so on the left hand side small a is constant, that drops out, minus B multiplied by dP dt minus of B multiplied by dt dt, which is just equal to 1, and on the right hand side you have alpha differentiated with respect to t, it will become 0, and beta multiplied by dP dt, and I take all the dP dt terms to the left hand side, and the coefficient of that will be beta plus B, and on the right hand side I take the constant terms, and that will become minus B. Okay. So, dP dt therefore will be minus B divided by B plus beta. I have divided both sides by B plus beta. So, this is the expression for dP dt, and this is negative because beta and B are positive. That basically means that as the tax rate rises, the equilibrium price falls. The rate of fall is given by minus B divided by B plus beta. Okay, you can actually imagine this in terms of a diagram that you have this P and suppose this is Q, and you have this supply function, this demand function. The demand function is shifting downwards as the T is rising, and therefore the equilibrium price is declining, right. So, that is it. Second part, so in the second part we need to find out explicitly the form of P. So, here implicitly I differentiated and I found dP dt, but suppose I find out explicitly what is the form of P, the equilibrium price, and then I find out dP dt. So, from the equilibrium condition, I use the equilibrium condition to find out first the equilibrium price. And if I simplify this, I am just skipping some steps. I get P is equal to A minus alpha divided by B plus beta minus of B divided by B plus beta multiplied by T. So, this is actually a linear function of T, right. First you have a constant term and then you have some coefficient multiplied by T. From the above, by differentiating both sides with respect to T, we get simply this minus B divided by B plus beta. This is what we have got earlier also by implicit differentiation. Here we did not use implicit differentiation, we explicitly found out the expression for P and then we got the expression for dP dt. Okay, finally, what is the last question? Last question is, if capital T is the tax revenue, find its expression and find the small t which maximizes the tax revenue. So, here we are looking at the situation from the point of view of the government. The government is getting some tax revenue, right. The total amount of tax revenue that it is getting, that is denoted by capital T. Now, suppose the problem for the government is it wants to maximize this tax revenue and it wants to earn the maximum amount of money that it can get from the market by imposing this tax on the consumers. Now, how does the government then fix the small t? Remember, the government has control over small t, that is the only thing that the government can do. So, the natural question arises, if the government wants to maximize the capital T, which is the tax revenue, then at what value of small t the capital T is getting maximized, right. So, the government will like to impose that rate of tax and that will generate the maximum tax revenue. So, therefore, we first find out what is capital T, the expression for capital T, and then try to answer the question at what small t it is going to get the maximum value. Now, what is the tax revenue after all? Tax revenue is after all the equilibrium quantity of goods that is being purchased and sold multiplied by the tax rate, right, because the tax rate is imposed on each unit of the good. So, the total amount of unit that is being sold and purchased multiplied by small t will give you the total tax revenue. Now, what is the equilibrium quantity? So, it is given by any of the expressions of either demand or supply, but these demands and supplies are evaluated at the equilibrium values. So, equilibrium demand and equilibrium supply. So, I just take the supply expression, which is alpha plus beta p, where p is the equilibrium price. Why p is the equilibrium price? Because I want to find out what is the equilibrium quantity that is being supplied and demanded, and that can be found out only at the equilibrium price. So, equilibrium price is already found. It is this that I have to use here. I have to substitute that here, and mind you, I have just broken down this term. So, it will be alpha multiplied by T plus beta multiplied by equilibrium price, which is A minus alpha divided by B plus beta, minus of B T divided by B plus beta, whole thing is getting multiplied by small t. So, our capital T, which is the tax revenue to the government, is this expression. Now, I have to simplify this expression a bit, and basically I get this by removing the brackets, and therefore, I get this expression T multiplied by alpha plus beta A minus alpha divided by B plus beta minus beta T multiplied by B divided by B plus beta. Now, the interesting thing to note is that this function, it is a function of small t. So, capital T is a function of small t, but it is a function where the form is such that it is t multiplied by another function of small t, right. So, t multiplied by something which is itself a function of small t. So, it is a quadratic function, so that is there. Now, if you will look at this function, then this function will attain the value of 0 at 2 points, at t is equal to 0 and at t is equal to this expression. So, it is like this. So, on the x axis you have the small t, which is the tax rate, and on the y axis you have the total tax revenue. And if you visualize this, it is like this. So, it is attaining 0 at point of origin and at this point, which is alpha beta plus A beta, A alpha b plus A beta divided by B beta, right. And so, it is a basically parabolic shape. So, therefore, the maximum is obtained at half of this. So, it is alpha b plus A beta divided by 2 B beta. So, that is why I have written, thus the maximum will be reached at this middle point, and the middle point's coordinate is this alpha b plus A beta divided by 2 B beta. So, therefore, we have solved the problem for the government. If the government imposes this small t, the rate of tax, then its total tax revenue will be maximized. Okay, so that concludes the lecture. So, just to make a concluding remark, in this lecture we have talked about the higher order differentials, higher order derivatives, and then we have talked about the fact that for partial derivatives also we can talk about the higher order derivatives, and there is this idea of a Hessian matrix related to that. And then we talked about the chain rule and implicit differentiation, and then we talked about the applications of these in practical economic problems. And so, let us conclude it here. Thank you.